Hello everyone. So let us continue our discussion on cationic polymerization. So in the previous video, we looked into the um, initiation step. Okay. So in this video, we will be looking into the propagation step in the cationic polymerization. So if we look into the cationic polymerization, to be exact, the propagation step basically involve as in the case of free radical, we have initially we had the suppose let me show it again for your clarification. So suppose this is your initiator, okay, and you have your monomer, vinyl monomer here, okay. So this reacts, okay, to form a initiator monomer complex, okay, CH2. Then you have your Cr2 positive, okay, with the corresponding counterion formed here. Okay, so this is the first step, that is the initiation step. Okay, now the next step is the propagation step. So propagation step, what happens? You have the CH2, you have the Cr positive with the corresponding counterions, which maintains the electrical neutrality, and then you have the other monomer, vinyl monomer here, which is again reacting here, okay, and we have the formation of your ECH2 Cr2, then you have the CH2, uh, then you have the Cr2 positive, okay, and you have the corresponding counterion here. Now the further propagating step, you have suppose n monomers, okay, reacting here to give ultimately your propagating chain with the corresponding counter anion. Okay, so this is kind of the propagation step that is happening in the cationic polymerization. Now, this particular step where the growing chain cation reacts with another monomer, it is not like a direct formation of a covalent bond between this end and this particular end of the two reacting species. It's not like that. It's not simply a covalent bond formation as we saw in the case of free radical. Free radical reaction, the growing chain radical just directly forms a covalent bond with the monomer. Okay, but here this particular combination where the propagating chain cation, propagating chain anion, okay, this, as you can see here, this is the propagating chain. When it reacts with the monomer, actually it involves two stages, okay. One of the stage is a formation of a pi complex, okay. This kind of forms a pi complex with the monomer, because we know vinyl monomer has a pi electrons, so it forms a pi complex with the monomer, which is kind of a very slow process. And then you have the direct formation of a covalent bond between the propagating chain and the incoming monomer. Okay, so this covalent, it's not a direct formation of covalent bond, but rather it involves an initial slow step where this propagating chain kind of forms a pi complex with the monomer, and this step is a slow process. So that means this is the rate determining step in this particular reaction. And here comes the effect of solvent. So if your solvent is having a very high solvation effect, that means it is able to solvate well the ions, what happens? This particular propagating chain, it would be solvated pretty well. So it would be kind of solvated well by the solvent. If your solvent dielectric constant is high, that means if it's a good solvent, then what happens? It will stabilize this propagating carbocation, thereby slowing this rate of the propagation step even more, because this pi complex, the positive charge is kind of dispersed. Okay, so this is not having that much ionic character to be solvated. So in this particular step, this part, that is the RHS part of the equation, the left hand side, the left LHS part of this equation is kind of stabilized. So reaction won't be moving so freely in the positive direction, that is in the forward direction. So that means if you have a very high solvating solvent present in this, if you use for polymerization of cationic, if you want to do the cationic polymerization in highly solvating solvents like polar solvents like water or methanol, for example, then you will retard the propagation step greatly because of this effect. Because here you are stabilizing the ion to such an extent that the pi complex formation would be, the rate of formation of this pi complex would be greatly reduced, and thereby this covalent formation would be reduced. And that is why the choosing of the correct solvent for carrying out ionic polymerization is pretty important. Another factor that that here causes a problem is that the as I told you, these propagating chain ion, okay, this propagating chain cation would have a counterion, okay, and the association with the counterion can be an intimate association, or it could be a solvent separated association, or it could be a freely solvated, highly separated ions. Okay, all these extremes can be possible. So if your solvent is having a very high solvation, then you will have formation of uh, uh, then you will have the formation of uh, these ionic species, these free ionic species, uh, uh, greatly happening. So if we have free forms of these ions present, then they can quickly react with the monomer and thereby carry forward the reaction. But we now know that even high solvation can also retard the propagating step because it is kind of affecting the formation of pi complex. So it is kind of an opposing factor here acting. In one case, the high solvation is causing the propagating step to be retarded because of the retardation in the formation of pi complex. Another case, if you're using too low solvating solvent, then what happens? You will have high intimate ion pair being formed. So what happens if intimate ion pair is formed? These cations are not freely available to attack a monomer. It is kind of hindered by this counter ion. So we have to always, whenever we do the polymerization using cationic polymerization or even anionic polymerization, it is essential that we check the polarity that we use for the solvent. Oftentimes, the solvent that is used is not solvents with high dielectric constant like water or methanol, but rather certain organic solvents like chlorinated solvents. Okay, chlorinated solvents, they are less solvating but highly polar. So such solvents can uh, help in separating this intimate ion greatly because of their polarity. They kind of hinder the interaction of this propagating cation with the counter ion, thereby freeing this carbocation enough to attack a monomer. Okay, so that is why choosing the solvent is very, very important when it comes to the ionic polymerization. So that is why the ionic polymerization is not very simple and straightforward as the free radical polymerization. We have to consider a lot of factors because that is why I'm saying that in this beginning I told you that the counterions play a very significant role in kind of affecting the mechanism of the reaction and thereby affecting the rate of the reaction. So every time when you do any reaction, the rate is very, very important. How you're getting, how fast you are getting, how much you are getting, all those things are pretty important whenever you are carrying out a reaction. So understanding of the mechanism, that is why very, very important in every reaction that you come across in organic chemistry. So Like in the case of the free radicals, we also have chain transfer reaction happening in the case of uh, cationic polymerization as well. Okay, and therefore this is another cause of a problem, because uh, this causes the chains to be abruptly terminated, and thereby we get polymers of low molecular weight. Because we studied what are the drawbacks of the chain reaction, we know that it causes low molecular weight, and then it also causes the formation of a polydisperse sample. Okay, so that is why this drawback even occurs in the cationic polymerization. So what are the ways in which it happens? One of the ways is the growing chain cation transfers its proton to the another monomer. So basically, you have the proton being released here, and thereby you form the double bond here. So you can imagine this like this: you have a CH, and it forms a double bond here, and a proton is released in the process, which is accepted by this monomer to generate a activated monomer here, and this get neutralized or terminated in the process. Another thing that we looked is similar to the self-biting. If you remember the chain transfer reaction, it's like a self-biting. So here what happens is that this cation kind of undergo electrophilic substitution at this end of this phenyl ring, and thereby forming this five-membered intermediate. It's pretty easy to understand if you consider these double bonds. It kind of undergo electrophilic. This is an electrophile, so it attacks here, okay, and forms a bond here. Okay, so this is this bond, and thereby you will have a positive charge, and in the process you will have, so this would be something like this. Sorry, here double bond and this double bond. Okay, so you have a positive charge developed here. So this will undergo movement like this. So H plus is generated here, and it becomes aromatic, and that H plus is accepted by this monomer, and thereby get activated in the process, and the chain also get terminated in the process. So these processes actually causing the premature abruption, premature termination of the growing chain, and that is why low molecular weight polymers are generated in the process. Other ways of happening is here you have a hydride abstraction happening to form a more stable ion. So basically, this propagating cation accepts a hydride from here. Okay, so because this particular hydride, okay, if it is removed, it generates a carbocation which is highly stabilized by not only hyperconjugation by these two groups, but also by resonance stabilization by this particular phenyl ring. So that also is another way in which this particular uh, so hydride is removed here, so it is accepted here to form a neutral species here, and thereby activating again this particular polymer. And this leads to another effect called branching. So this kind of chain transfer lead to branching. So now the growing chain would be in this direction. So you have a linear polymer, and then you have a branching happening because of this kind of hydride abstraction. Another thing is by with the solvent. So solvent, if you have solvents such as benzene, okay, they so here they can undergo electrophilic substitution again. So when it undergo electrophilic substitution, you have this carbon attached here, and in the process you have a H plus released here, which is accepted by this monomer, and in the process getting uh, activated. Okay, so these are the various ways in which chain transfer can happen in the cationic polymerization, and this is a very much a problem as the problem you see in the free radical polymerization. So we will talk about how to stop or kind of reduce this chain transfer reaction in the next slide. But let me introduce to you the termination step Okay, termination is basically you have the propagating chain reacting with the counterion to form a covalent bond and thereby getting terminated. Or if you are using some Lewis acids like this, they actually react with the Cl to form this kind of termination. In the process, they form a Lewis acid like this. Okay, so this is just a combination of the chain end with the counterion is what we see in the termination reaction. But often what is happening is that the chain transfer process is happening too often in this cationic polymerization that this termination step is kind of reduced. The proper termination doesn't happen. Often the termination happens via chain transfer reaction. So that is why it's not so exhaustively happening because in the reaction mixture because of the chain transfer reaction. So how to stop this chain transfer reaction so that we can stop the polymerization in via cationic polymerization in normal fashion and a normal terminating fashion. Okay, so let us look into how we can do that. So for that process, actually, we use certain tertiary butyl pyridine. Okay, so this is, if you name this as, so if you start numbering from here, 1, 2, 3, 4, 5, 6. So it is 2,6-ditertiary butyl pyridine. Okay, so it is 2,6-ditertiary butyl pyridine. So what happens is that whenever the chain propagating propagating chain cation uh, tries to lose a proton. Okay, try to lose a proton. This will quickly accept that proton. Okay, this particular organic moiety, if it is present in the reaction mixture, it will quickly accept the proton and thereby prevent it from reacting with the other species in the reaction mixture like solvent or monomer or another neutral polymer. So thereby, even if any of the propagating chain is showing some tendency of losing the proton, this will quickly trap that proton, thereby preventing that proton to be reacting with a monomer or with another phenyl ring or solvent or anything. Okay, so thereby this acts as a trap. So this is kind of a proton trap. That is why it is called a proton trap. So it intercepts the proton before it transfers to the monomer, thereby preventing the unnecessary activation of the monomer. Because whenever we use initiator in certain concentration, we want a limited number of monomers to be activated, right? Only then we'll get long chain polymers. But if this unnecessary chain transfer happens, which unnecessarily activate a particular monomer, then it causes unnecessary chain with lower molecular weight. So that is a great problem. So preventing that could be by addition of these proton traps, in this case 2,6-ditertiary butyl pyridine, okay, which we can use. So what is the effect of this? Though the overall yield might be low when we use this kind of trap, but the molecular weight that we get here is pretty high because here it is not causing unnecessary loss of the monomer because of this chain transfer process. And another thing is low polydispersity index. So rather than getting a broad molecular weight distribution, we will get a sharp molecular weight distribution. And always polymerization, we aim for lower polydispersity index graph. Now, these particular terminologies you will understand when we will do a video on molecular weights in the later module. Okay, so just remember, we always prefer to have a monodisperse or a lower polydisperse index. Okay, that is more preferred always for a polymerization process, but often we during synthetic process we usually end up in a much broader polydispersity index. So this is one way of kind of preventing the chain transfer reaction happening, okay, by use of proton traps. Now, another way in which we can actually kind of use to our advantage this chain transfer reaction is by kind of use of uh, certain molecules, certain bifunctional molecules, which are called as the Iniferes. Okay, so Iniferes, a bifunctional molecule called Iniferes, which brings about both the initiation and the chain transfer reaction. Both are happening in the. So here we have in the Inifer brings about both the initiation as well as the chain transfer reaction. Now, what is the advantage of this is we can by the use of the chain transfer problem in the cationic polymerization, we actually are making a, a different kind of polymer which is called as telecalic polymers. Now telecalic polymers are basically polymers with active end group. Okay, now what do you mean by active end group? uh, what I mean by saying active end group is that if you have an active N group present in a polymer, this polymer can be uh, polymerized further if you add a monomer. Okay, so this is kind of a live polymer. Often the polymer that we have discussed about the vinylic polymers, they are kind of after termination, they are dead. Okay, you cannot further polymerize them. But these telecalic polymers means those polymers which have an active end group. Okay, so if we have an active end group, these can be used further to carry out the polymerization process. Okay, so that is what mean by telecalic polymer. Now usually polymers with active end groups, they come under the category of living polymers. They are coming under the category of living polymers. So one of the type of living polymer is telecalic polymer. So telecalic polymer, what is the characteristic of telecalic polymer? So this is a telecalic polymer. This is an example of telecalic polymer. So here what you see is the end groups are pretty same. Okay, so in this telecalic polymer, the importance is it's a bifunctional or it's having a bifunctional moiety, and these bifunctional moieties are same bifunctional end group. Sorry, let me use the term that. So in telecalic polymers, the end groups are active, and these end groups, these active end groups are same. Okay, so whenever living polymers have same active end groups, they are classified under the category of telecalic polymers. So now Iniferes are molecules such as this. Okay, in this case, so it is alpha dash. So it is alpha dash dichloro isopropyl phenyl. Okay, phenyl compound. Okay, now this particular compound, okay, with bifunctional grouping are called as Iniferes because they participate in both the initiation and chain transfer reaction leading to the formation of telecalic polymers. So let us look into the mechanism. So what happens here is, so this is kind of initiator and this is your co-initiator. So this is your co-initiator. Okay, sorry, the spelling didn't come right. So it is co-initiator. Okay, so co-initiator, this is a initiator. So when it reacts with Lewis acid, it will accept a Cl minus to form BCl4 minus, and in the process, a carbocation is generated. So this is your initiator. Okay, this initiator reacts with the monomer to form initially the initiator monomer complex, and then further monomer it reacts to form a propagating chain. So this is the propagating step. So this is the initiation. First step is your initiation. Okay, and then this is your propagation step. So it involves both the initiator monomer complex and plus the propagation. So it is a propagation step. So second step is the propagation step here. Okay, now third step, basically what is happening is this propagating chain, this is a propagating chain, kind of loses the a proton, or it kind of transfers its reactivity. That means reactivity means it will lose its cationic character. How it loses its cationic character? Rather than losing a proton here, what it does, it will accept a chloride ion from this Inifer molecule, that is means bifunctional molecule, it will accept chloride ion and thereby getting deactivated in the process or terminated in the process. So this chain transfer reaction in a cationic polymerization can happen by proton transfer, or it can happen by accepting of a negatively charged species from another moiety. So one of the case that we studied was the accepting of the hydride radical. Okay, now hydride ion. Okay, so here chloride ion is being accepted from this Inifer molecule. Okay, and in the process this chain got terminated, and you have a activating site generated here, which can further react with the monomer. Okay, similar way you can have terminate chain transfer happening at this end of the Inifer, and you can have propagating step happening here as well. So when this chain transfer reaction happen on the Inifer molecule, we have the generation of a telecalic polymer with an active end group. Why I'm saying active? So here you have the Cl moieties here. So if now you add BCl3 and add monomer, this can further be activated to participate in polymerization process. Okay, so here what you see is this Inifer, this bifunctional molecule here, alpha alpha dash dichloro isobutyl benzene. Okay, diisobutyl benzene. This particular compound is kind of acting both as initiation, okay, and also kind of help in the chain transfer reaction, leading to a constructive use of chain transfer process. So constructively, you are able to use the chain transfer process in this case to generate a more vivid and more useful polymers like telecalic polymers. So thereby this, if you use certain Inifer molecule, that means bifunctional molecules. One of the example is this one. The exact name of this molecule, let me give you, otherwise you will confuse it. So it is alpha alpha dash dichloro. So alpha, so this is alpha group, alpha alpha dash, because it's the same type of group, so it is called alpha alpha dash dichloro diisopropyl. So this is isopropyl group. So diisopropyl benzene. So I have correctly said you the name. So it is alpha alpha dash dichloro diisopropyl benzene. Okay. So this is one example of the Inifer molecule. Inifer molecules are basically bifunctional compounds which brings about both initiation as well as chain transfer. So here one part of the work of the Inifer molecule is initiation. So it is kind of participating in the initiation of a polymerization process. And another work that the Inifer molecule does is it helps in the chain transfer process, and thereby help in the generation of a useful living polymer of the type telecalic polymer. Okay, so that is one way is that we can stop chain transfer reaction by using proton traps. Another is we can use chain transfer to our advantage by use of these kind of bifunctional molecules called Inifer. And this Inifer name actually is coming from that the work that it does. That means it does the initiation, that is INI, and then it also does the chain transfer. So this fer. So that from this, that it performs both initiation and chain transfer, this terminology called Inifer came into being. So this is kind of a Inifer method of utilizing chain transfer for creating telecalic polymers. So I hope you understood this particular thing pretty clearly. Lastly, I would like to introduce you kind of pseudocationic polymerization, because sometimes when you use perchloric acid, okay, like HClO4, okay, as a initiator in the process, what you found is that often the rate is pretty low. That means it undergoes very slowly. So when we studied the mechanism of how this polymerization process is happening, we found that often the propagating chain is kind of covalently linked with the counterion. So counterion in this case is nothing but ClO4 minus. So the covalent linkage is kind of retarding the rate of the polymerization when we use perchloric acid as a initiator. So this kind of polymerization, where rather than the proper cation and the counterion being formed, it is a kind of a covalent linkage that is formed here, or an intimate. Another reasoning that was said is that an intimate ion pair is formed. So that is why the reaction rate is pretty slow, because of the problem of the reaction of this end with another monomer, because of the hindrance provided by this counter ion, or by the strong nature of the bonding between the chain end and the counter ion. So since there is no proper carbocation cation that is formed, that's why it's called as pseudocationic, though it is a cationic polymerization because it involves the addition of proton. But the propagating chain usually doesn't have much of a cationic character. That means more of a covalent bond is formed here. That is why it's called as a pseudo-cationic polymerization, and the reaction proceed at a much slower process, because obviously when there is an intimate contact between the counterion and the propagating chain, then the polymerization rate would be greatly reduced. That is what we discussed initially, that solvation, how the intimate pair is being freed if we use proper solvating solvents. So I hope you got a pretty much understanding about the cationic polymerization. So in the next video, we will be discussing about the ionic polymerization. So I hope you have pretty much understood in detail the cationic polymerization. So thank you very much for your attention.